Hi, so we're going to talk about 8.5, which is quadratic functions and transformations. And there's two different formats equations are given for quadratics, meaning highest exponent is 2. The shape becomes a parabola. So they can either be in what's called standard form or vertex form. And sometimes it's actually technically in both simultaneously, as you'll see on the first couple examples here. So our parent quadratic, just with its vertex or its key point being at 0, 0, that's what makes it a parent. And it's got a standard shape for it opening up, meaning the A is 1, is shown here. So it's just x squared. Once you start adding or subtracting or multiplying or dividing to that, then it's not a parent anymore. But they're related. So I have here the standard form for a quadratic and the vertex form. You can find the vertex from either way, and the vertex is pretty critical to graphing, especially using the XYZ system, because you'll have to graph the vertex and some other point. And we'll talk more about that in the 8.6. So if you need help with the vertex, kind of have to go forward a little bit. There's that vertex formula, x equals negative b over 2a, that is used to find the vertex when it's in standard form. The vertex when it's in vertex form is just hk, the opposite of what's showing, and then what's showing. So I just did a standard t-table, which is great if you don't know what the shape is going to look like. You can just always do a t-table. Sometimes you're going to get values that don't fit on your graph. So if I had done like 0, 1, 2, 3, 4, 4 would have been off my graph. On some of the XYZ graphs, even 9 is off of it. And that gives you kind of a hint that you should then go the other direction. In XYZ, you just do 2 points again, the vertex and one other. But if you're doing this by hand, you really want to have at least 3 points. You want the vertex and at least a point on either side, ideally. When you take your parent, x squared, and you multiply it by 2, the y is equal to 2 times what it was before. So it's twice as much. So the y is twice as much, meaning the height is twice as much. So you can see here's the parent graph highlighted in yellow. And the height was here 1 from the axis. The green, when it was an A of 2, is 2, twice that. Here it was 4, then with the green it's 8, twice that. If your A is a half, it'll be half as high. So that's instead of 1, it's a half. Instead of 4, it's at 2. Instead of 9, it's at 4.5. So that the A contributes to how narrow or how wide it is in comparison to the parent. So the parent is when A is 1. When it gets bigger than 1, it gets narrower. When it's less than 1, it gets wider in comparison. We also call that being stretched and being compressed. So you can see that with the t-table, how that works. And you'll notice that these t-tables were centered around 0, 0. And that's pretty typical to have, -3 to 3 on t-tables and adjust from there if it doesn't fit or doesn't capture the vertex. But you'll notice this does capture the vertex. There's symmetry about that point. So the vertex really is at 0, 0, as you can see. And that's because we haven't added or subtracted anything. So we haven't shifted it right or left or up or down. That's what adding and subtracting does. So the point of this first row, or this first area here, is to talk about the A being positive and just how it affects the stretch or compression of it. When it's a negative, what that does is it just multiplies it all by a negative. So it's going to flip it all below the x-axis. So it's going to be opening downwards. That's called orientation. So it's going to have a downward orientation. But still, it's going to be narrower when it's when the absolute value is more than 1. So the negative just refers to it being opening down. The 2 is still more than 1. Or you can think of it as the absolute value, which is 2, would be more than 1. I have a kind of a summary of how that works in terms of stretching, being normal, being compressed, and the orientation being up or down, whether the A, which is the leading coefficient. So let me talk about the A for a moment in terms of the equations. It's the leading coefficient. It's the one that goes with the highest exponent when it's in standard form, and it's the value in front of the parentheses when it's in vertex form. So when things are in vertex form like this, then and you can see here I have some addition and subtraction going on. That's shifting your parabola right or left, up or down. In this case, because it's associated with the x before it's being squared, that's affecting the x direction, the horizontal. So that's a right or left. And it turns out, as I mentioned before, the h, it's like the opposite of what's showing, so -3, so it's 3, 0. And you can see that if you did a t-table, your vertex is at +3, 0. That's where you have the symmetry about it. So you can see that there's symmetry about that vertex. You can see it from the t-table as well as when you graph it. The A is an invisible 1 here, so it's going to have the same pattern, the same shape as before. And let me talk about that shape again a little bit more back up here. We talked about how 2 is just twice as high, but the parent, how do we get the parent? The parent is just you squaring. So if you go over 1 from the vertex, then you're going to square 1 and get 1. If you go over 2 from the vertex, you're going to square 2, which is 4, and go 4 up. 3 over, then 9, because 3 squared is 9. And it's just because it is the parent graph, it's just what the x is being squared. Even a negative, when you square it, becomes positive. And that's why it goes up on the other side of the vertex. So back to this one, if we saw that the vertex is 3, 0, and we realize that the A is 1, we can then plot our vertex at 3, 0, and go over 1 from the vertex and square that. 1 squared is 1, so 1 up. 2 over 4, because 2 squared is 4. 3 over from the vertex, 9, because 3 squared is 9. You can see that that's that same pattern. From the vertex, we went 1, we went 4, we went 9 up. When you are subtracting after being squared, then that's affecting the y value, because y equals this, just -5. So the y is now 5 less than the parent. So the y, the height, is 5 fewer than the parent. So it's going to shift the parent graph down 5 units. So the vertex will be at 0, -5. You can rewrite this potentially fairly easily in terms of vertex form. Other times it's not quite so easy. It just depends on how involved these are. If there's a b term, then you're going to have to do completing the square, which we'll briefly show in the next lesson as well. But this one is pretty easy to, because there is no b term, to recognize that this is x minus 0, because that's x squared minus 5. And so it can be written as in vertex form. The vertex, again, being the opposite of this, opposite of 0 is just 0, and then keep that the same, -5. And the A being 1. Alternatively, you could do a t-table, and what you'll realize is that your vertex, where it's centered about, is 0, and it would be -5. When you plug in 0, you would get -5, and then you can plug in points on either side of 0. And so you'll see that you'll end up getting these points that are in green here. If you did the vertex way, plot the vertex 0, -5, and since the A is 1, you're going to go over 1, square 1, you get 1, over 2, square 2, you get 4, over 3, square it, you get 9, and that makes the shape for a parabola where the A is 1. This next one is where the A is 2, and we have changed in the x direction and in the y direction. So the x has been affected, and again we do the opposite, so -3, and the y has been affected. Keep that the same. So the vertex is at -3, -7. We have shifted to the left 3 and down 7 from the parent. Now the parent would be over 1, up 1, over 2, up 4, over 3, up 9. But we are doubling those y's, doubling those heights because the a is 2. So we're going to go over 1 and up 2. Over 2, and instead of 4, we're going to actually go twice that, 8. Now in XYZ, all you need is the vertex and one other point. So it's always 1 and then whatever your a is, because it's going to be 1 times a. So it's going to be a. Here it's always 2 and then 4 times your a. So in this case, 4 times 2 was the 8. Similarly, we have this one here. This one is -1/2. The negative means it's going to open downward. You're going to go half the height you would normally go, so it's going to be compressed. In the x direction, we're going to be going right 3, again opposite, and then we're going to go down 2. So right 3, down 2 from the origin. My parabola is going to be opening downward because of the negative in front of the, at the beginning of it for the a. Go over 1 and go down 1/2, your a amount, or half of 1, so it's half. Over 2, you would normally go 4, you're going to go half of that, so you're only going to go down 2. Over 3, you would normally go 9, you're going to go half of that, so 4 1/2. But again, in XYZ, you'd plot the vertex and one other point, going over 1 and however much your a is. If it's negative, you're going to go down 1/2 if it's 1/2. If it was a -3 here, you'd go over 1 and down 3, etc. So a little table here, and again, it's from the vertex going over 1, right and left from the vertex, 1 unit. You would go up if it's positive, you go down if it's negative, 1 unit. Go over from the vertex 2 places, you'd go either up or down 4 units. 3 places from the vertex to the right and the left, you would go up 9 units if it's positive, or down 9 units if it's negative. If it's 2, you do twice that. So instead of 1, it'd be, instead of 1, it would be 2. Instead of 4, it would be 8. Instead of 9, it would be 18. Or if it's a half, you just do half of those. So half of 1, half of the 4, half of the 9, half of the 16, etc. And normally, only a couple of these will actually fit on your graph. So that is 8.5. There's more to come on vertex in lesson 8.6, as well as just graphing, more on graphing in 8.6 and more on vertex.